Hello friends, myself Jitendra Kumar. I am taking electrical machine design for 8th semester, 7th semester electrical engineering students. In the previous lecture, we are discussing about the electrical machine design and discuss the various parameters which are associated in, with the design of electrical machines. Under this, we are discussing about the electrical engineering materials, what are the space factor, choice of specific electrical and magnetic loadings, thermal consideration, heat flow and temperature rise. Now, next we are discussing about the rating of the different types of DC machines, AC machines, then the standard specifications which are associated with the machines and what are the manufacturers of different types of machines are there. Now we are discussing about the DC machines, their output equations and the main dimensions under this lecture. This will be the structure of the armature and this is the structure of the field winding or the stator. This will be the rotor and this will be the stator. So over the stator you are finding that there is a yoke. Yoke is the outer part of the machine. These are the poles. These are the interpoles are there. These are the main part of the machines and there is a winding which will be placing over there. Interpoles will be the supporting poles which will be associated with the machine so that the losses of the machine will be minimized. And this part will be we are indicated at this will be the rotor part of the machine where the windings will be placed under this one, and this part will be the commutator part, and this is the rotor part of the machine. So the size of DC machines depends on the main or leading dimension of the machine, like the diameter of the armature, what is the diameter of armature is there, and the length of the armature core. As the output increases, the main dimension of the machine D and L also increases, and it will be decreases as the machine rating will be reduced. This will be the side view of the machine. Over here you are finding that the number 3 will be the armature part, which will be a rotating part of the machine. Number 2 will be the DC poles, and number 1 will be the yoke of the machine. And if we are looking on this side, we are finding that the third one will be the armature, and number 4 will be indicated as a commutator part. Commutator part will be the converter and converter of the AC supply into DC or the DC supply into a AC one. And the number 1 will be indicated as a yoke part of the machine. And if whenever in the previous slide we are discussing that the D and L of the machine will be associated with the rotor part. So this part it will indicate as a diameter of the rotor, that what is exactly the diameter of the rotor, and the length of the rotor, that what is the length of the rotor is there. So on that basis we will define that the size of the machine it will be changes. It will be increase or decrease. The output equation and the main dimension of DC machine, there will be some parameter which we have to just take as a constant. So output equation relates the output and main dimension of the machine. Actually, it relates the power developed in the armature and the main dimension. So here we have the some constant. Capital E is the EMF induced or back EMF. We are taken about the DC machine, not a motor or generator. So if EMF induced, it usually takes place in the case of the DC generator, and back EMF is the concept related with the motor. IA as the armature current, phi is the average flux per pole, Z is the total number of armature conductors, N is the speed in RPM, P is the number of poles, A stands for the number of armature paths or circuits, D is the diameter of the armature, and L is the length of the armature core. So that at that moment we are finding that the power developed in the armature in kilowatt it will be E times IA. E is the EMF or IA is the armature current times 10 to the power minus 3 if we are denoted in kilowatt. So this relay sign will be converted as the EMF E will be changed by the phi Z N P upon 68 into 10 to into IA into 10 to the power minus 3. P phi it will be replaced by E phi into IA Z upon A into N into 10 to the power minus 3 by 60. The term P phi represents the total flux and is called the magnetic loading. So the magnetic loading per unit area of the armature surface is called the specific magnetic loading or average value of the flux density in air gap B average. That is B average equal to P phi by A or pi dr Web per meter square or Tesla denoted by T. So average flux density will be not unit as a Tesla. Therefore, P phi equal to B average into pi dr. The term IAZ upon A represents the total ampere conductors on the armature and is called the electric loading. Electric loading or per unit length of the armature periphery is called the specific electric loading indicated by the Q. That is Q equal to IAZ upon A times pi d. Ampere conductors per meter. Therefore, IAZ upon A equal to Q pi d. Substitution of equation 2 and 3 in equation 1, it leads to kilowatt equal to V average pi dr into Q pi d into pi into N into 10 to the power minus 3 by 60. So it will be comes out 1.64 into 10 to the power minus 4 V average Q d square L into L. C naught d square L n, where C naught is called the output coefficient of the DC machine is equal to 1.64 into the power minus 4 V average into Q. Therefore, d square L it will be kilowatt per 1.64 into the power minus 4 V average Q and meter Q. The above equation is called the output equation. The d square L product represents the size of the machine or volume of iron used. In order that the maximum output is obtained per kg of iron used, d square L products must be as less as possible. For this, the values of Q and V average must be high. Now we are discussing about the effect of the higher value of Q. Since armature current IA and number of parallel paths A are constant and armature diameter D must be as less as possible or D must be a fixed minimum value. The number of armature conductors increases as Q equal to IA 0 upon A pi D. It will be increases as Q increases, the number of conductors increases, resistance increases, so I square R loss increases, and therefore the temperature of the machine increases. Temperature is a limiting factor of any equipment or machine. Secondly, as Q increases, the number of conductors increases. Conductors per slot, it will be increases. Quantity of insulation in the slot increases. Heat dissipation, it will be reduces. Temperature increases. Losses increases and efficiency of the machine also reduces. As Q increases, number of conductors increases. Armature ampere turns per pole per it will be increases. Flux produced by the armature increases and therefore the effect of armature reaction it will be increases. In order to overcome the effect of armature reaction, field error has to be increased. This calls for additional copper and increases cost and size of the machine. As Q increases, number of conductors and turns increases, reactance voltage proportional to turn square increases. This leads to sparking at the combustion. Naturally, the effect of higher value of B average. As B average increases, core losses increases, efficiency reduces. As B average increases, degree of saturation increases. MMF required for the magnetic circuit increases. This calls for additional copper and also increases the cost of the machine. It is clear that there is no advantage gained by selecting higher values of Q and B average. If the values selected are less, then d square L will be large or the size of the machine will unnecessarily be high. Hence, optimum value of Q and V average must be selected for deciding if designing a DC machine. In general, Q lies between 15,000 to 5,000 ampere conductors per meter. Lesser values are used in low capacity, low speed and high voltage machines. In general, V average lies between 0.45 to 0.75 Tesla. Next, we the separation of D square L product. Knowing the values of Kw and N and assuming the values of Q and V average, a value of D square L, it will be D square L equal to kilowatt per 1.64 into 1 minus 4 V average Q and can be calculated that it be 0.1 meter cube. Since the above expression has two unknowns, namely D and L, another expression relating D and L must be known to find out the values of D and L. Usually a value for the ratio armature core length L to pole pitch is assumed to separate d square L provided. The pole pitch tau refers to the circumferential distance corresponding one pole at diameter d. In practice, L upon tau lies between 0.55 to 1.1. Therefore, L equal to 0.55 to 1.1 tau, 0.55 to 1.1 pi d pi p. If L by tau equal to 1 and p equal to 4, then automatically the L equal to 1 into pi d upon p. 1 into pi d upon 4 means 0.785d. Therefore, d square equal to d square into 0.785d equal to zero point 0.1 or d equal to zero point 0.5 meter. Thus, L equal to 0.395 meter. Now, d square L product can also be separated by assuming a value for the peripheral speed, peripheral velocity of the armature. So this will be the dimension of the DC machine, and now we will discuss about the other parameters associated with the DC machine and design or manufacturing.